We will now talk about the resistance of a conductor. What are the factors on which the resistance of a conductor like this depends on? Well, does it depend on the current? Conductors that obey Ohm's law are called ohmic materials. And for such materials, the resistance does not depend on the current passing through them, but depends only on the material of the conductor. Most conductors are ohmic when the temperature remains a constant. That means when the temperature changes, the resistance will change. So one factor that is going to make a difference in the resistance is going to be the temperature. The other factors are the physical factors of the conductor, which we will talk about in a minute. Resistance of a conductor depends on physical factors such as length of the conductor, area of cross-section, and temperature T. Now tell me, what happens if I increase the length of the conductor? Well, if I increase the length of the conductor, electric charges have to drift through a very long path. That means the resistance is greater. You see, if you have a very long corridor and a large number of people have to pass through it, as the length of the corridor increases, it will be much difficult for the people to reach the other end. So we can say resistance is directly proportional to the length of the conductor. Now, how does the resistance is affected by the area of cross-section? Area of cross-section is a measure of how thick the conductor is. If the conductor is very thick, the area of cross-section is large. Tell me, a large area of cross-section, will it increase or decrease the resistance? Let's go back to the analogy of the corridor. If you want to make it easy for the people to pass through a corridor, we better make the corridor wider. Is that right? Make it easy for people to go. So as the area of cross-section increases, it will be easier for electric charges to drift through. The resistance decreases. And so the resistance of a conductor varies directly as the length of the conductor and inversely as the area of cross-section. And of course, the resistance also changes with temperature. We will consider these two things differently, the physical factors and then the temperature. The resistance of a conductor is directly proportional to its length and inversely proportional to its area of cross-section. How do we write that mathematically? You can write it as R is, I haven't written the proportionality here. You can see this can be written as R is proportional to L over A, or R equal to a constant times L over A. So this is a constant for that particular material. Resistance of a conductor equal to a constant times length divided by the area of cross-section, where rho is a constant and it is called the resistivity of the material, the resistivity. Can you tell me the unit of measuring rho? You can see if you solve for rho, rho will be RA divided by L. The unit of resistivity is ohmmeter. Can you get that from here? RA, ohm meter squared divided by meter will give you ohmmeter. So resistivity is measured in a unit called ohmmeter. How does the resistance depend on temperature? As the temperature increases, the amplitude of vibrations of the atoms and molecules of the conductor will increase, which will make it difficult for the charges to drift through. That means as temperature increases, the resistance also will increase. Conversely, if you decrease the temperature, what will happen? A decrease in temperature will create more order within the material. There will be, the atoms and molecules will be more quiet. That means it will be much easier for charges to drift through. In fact, there is a study, a branch of physics called low temperature physics. And at very low temperatures, most materials will lose all resistance. At that time, when a material loses all resistance, it becomes a superconductor. In other words, no energy will be lost in transporting electric energy through those conductors. You know, a lot of energy is actually lost in transporting electricity from one place to another. You know, these big cables, the high voltage cables, the high tension cables that brings electricity to your local area from the place where it is generated. Now, they are resistance wires. Although they are good conductors, they offer resistance for the flow of electric current. That means a lot of energy is actually wasted in overcoming the resistance. If you can get those cables made of superconductors, a lot of that energy can be saved. Well, the science of producing superconductivity is superconductivity at low temperatures. Well, at the moment, superconductivity can be obtained only at very low temperatures. There are researches going on to see if we can find materials that will be superconducting at room temperature. Then we can solve that problem. And maybe some of you can take that challenge and do that research so that we can have materials that will be superconducting at room temperature. The temperature dependence of resistivity is nearly linear for all metals, except at very low temperatures. Now, the resistivity of a material at any given temperature is usually compared to its resistivity at 20 degrees Celsius and is given by the relation rho. Remember, this is the equation for the resistivity of the material. Rho equal to, that means rho at any temperature T. The resistivity at any temperature T equal to rho 20 times 1 plus alpha T minus 20, where alpha is a constant called the temperature coefficient of resistivity. A similar equation can be written for resistance. You can see resistance and resistivity. Resistance at any given temperature R is R20, means resistance at 20 degrees Celsius times 1 plus alpha times T minus 20, where alpha is called the temperature coefficient of resistance. Now here, alpha is a constant called the temperature coefficient of resistivity or temperature coefficient of resistance. Now, I have got some values of these which will be useful. I have given you the material and the resistivity at 20 degrees Celsius. So these are the values of the resistivity of some common materials like copper and aluminum. They are the most commonly used conductors. So those values are important. The resistivity of aluminum is 2.8 times 10 to the negative 8 ohm meter. And the value of its temperature coefficient of resistance is 3.9 times 10 to the negative 3 per Kelvin. And similarly for copper. We may need it when we want to use them for problem solving. Alright, let's do a problem. A resistor constructed of nichrome wire has a cross-sectional area of 2.4 millimeter square. When a potential difference of 12 volt is applied across the ends of the resistor a current of 0.0056 ampere exists in the resistor. What is the resistance of the resistor? What is the length of the resistor? Well, to calculate the resistance, we need the potential difference and the current. Is that right? When a potential difference of 12 volt is applied, there is a current of 0.0056 ampere. Can you calculate the resistance? Yes. Alright, we will start by calculating the resistance. The area of cross section of the wire is given as 2.4 millimeter square. That is 2.4 times 10 to the negative 6 meter square. I hope you understand that conversion. The potential difference is 12 volt and the current is 0.0056 ampere. The rho for nichrome, I picked it from the table. Rho for nichrome is 100 times 10 to the negative 8 ohm meter, and those are our data. Now, in part A, what is the resistance of the conductor? R equal to V over I. V is 12 volt, I is 0.0056 ampere, and that gives the resistance of that conductor or that resistor as 2142.9 ohm. Alright, B, what is the length of the resistor? Well, we now have to recall the equation that connects the resistance of a conductor, how the resistance is related to length, area of cross section and resistivity. Can you recall that equation? R equal to rho L over A. So R equal to rho L over A. We have the resistance, we just calculated. We have the length, we have rho, is that right? We have the area of cross section, therefore we can calculate L. Solve for L. L equal to RA divided by rho, and put all those values that we have. That will be 5,143 meter. The length of that resistor is more than 5 kilometers. Alright, let's do another one. A wire with a resistance R is stretched to twice its original length. What is the resistance of the new wire? For example, if this is the original wire, you apply a stretching force and stretch it to twice its length. What happens when you stretch the wire? Its thickness will reduce, right? Okay. Well, let L be the length and A1 be the area of cross section of the original wire. So the original wire has the length L and the area of cross section A1. Then the volume of the wire. How do you find the volume of the wire? Volume will be length multiplied by the area of cross section. So area, or the volume, not the area. The volume of the wire will be length multiplied by the area of cross section, A1 times L. Now after stretching, its length is 2 times the original length. And its area of cross section obviously is smaller now. Let that area of cross section be A2. What is the new volume? The new volume will be 2L times A2. Is that right? Yes. So the volume of the wire now is V equal to A2 times 2L. Now are these two volumes different? By stretching the wire, have I changed the volume? No, the volumes are the same. That means this volume A1 times L equal to this volume that is 2A2 times L. So because the volumes are the same, I can now write A1 times L equal to 2A2 times L, and that gives us a relation between A1 and A2. A1 divided by A2 equal to 2. Now we can now use this to calculate the new resistance. What is the resistance of the wire when it is stretched? Well, we keep this value A1 over A2 equal to 2. Before stretching, its resistance is R, and let's write down a relation for that. What does R depends on? R equal to rho L over A1. Is that right? Yes. So original resistance before stretching, its resistance is R, that R equal to rho L over A1. That means I can now solve for L from there. That is L equal to R A1 divided by rho. Now, after stretching its resistance, let's call it R prime. Can you write a similar relation for R prime? What happened? This length L becomes 2L, and this area of cross section is now A2. So that resistance R prime equal to rho times 2L. This length, the length has become twice the length, and the area, the new area of cross section is A2. So this is the new resistance R prime, and this is what we want to find. Well, all I need to do is I'm going to replace this L. You see, I colored it red. What is that L equal to? We have it here. L equal to R A1 over rho. So replace that L as R A1 over rho. And what you have now in here, that will be 2 times R. Look at this. Rho and rho will cancel. We don't need the value of rho. That will be 2R times A1 divided by A2. So R prime equal to 2R times A1 divided by A2. Okay. Well, we know A1 divided by A2. A1 divided by A2 equal to 2. Therefore, R prime, the resistance of the wire after stretching, is 2 times, well, 2R times A1 divided by 2 is 2. And that gives you 4R. So, when a resistor of length L is stretched to twice its length, its resistance now is 4 times the original resistance. Alright, I hope you understood the way I solved this problem. Look through it one more time. Another problem. A conductor of uniform radius 1.5 centimeter carries a current of 5 ampere. If the electric field in the wire is 150 volt per meter, what is the resistivity of the material? Well, so a conductor of uniform radius 1.5 centimeter carries a current of 5 ampere. The electric field in the wire is 150 volt per meter. What is the resistivity of the material? Now, what other things we have? Resistance R, the radius R of the wire is 1.5 times 10 to the negative 2 meter. What else do we know? If the radius of the wire is 1.5 times 10 to the negative 2 meter, what is the area of cross section? Area of cross section is pi r squared, and that will be pi times the square of the radius. That gives me 7.1 times 10 to the negative 4 meter squared. So we know the area of cross section of the wire. We know the current in it, I equal to 5 ampere, we also know the electric field in the wire. Well, if you know the electric field in the wire, which is 150 volts per meter, what will that lead us to? Do you know that the old equation we have, E equal to dV over dr or dV over dx. That means dV, the potential difference, is electric field times the length of the wire. The dx is the length of the wire, because potential difference is between the two ends, and the length of the wire, delta x, is between the two ends of the conductor. Well, E equal to 150 volt per meter. Let the length of the conductor delta x be equal to L. We don't know the length, so delta x, the length of the conductor, be equal to L. Then this is delta x equal to L. The electric field E in the conductor is, alright, one more time, what's the equation? E equal to delta V over delta x, which is V over L. So the electric field in that conductor is potential difference between its ends divided by the length L. Now, if V is the potential difference between the ends of the conductor, then that V equal to E times L. Is that right? If this V is the potential difference across the ends of the conductor, that V will be equal to E times L. And E is given to be 150 volts per meter, and L we don't know, so we leave it like this. So we've got the value of V. Well, look at this. We know the current in the conductor. We now know the potential difference across its ends. What will that lead us to? You got the current, we got the potential difference. Therefore, what other information can we obtain using that? We can find the resistance of that conductor. Alright, so the voltage is 150 L volt. Alright, the current is 5 ampere. The potential difference is 150 L volt. Therefore, the resistance of the conductor is R equal to V over I. And what is the V, the potential difference we obtained? 150 L volt. The current is 5 ampere. Therefore, the resistance is 30 L ohm. You can see we don't know the length of that wire, so we keep that length. 150 L volts divided by 5 ampere is 30 L ohm is the resistance. What are we looking for? Well, we are looking for, well, I forgot what we're looking for, but we know that we are now in the territory where we use the resistance of the conductor to figure out whatever we are looking for. R equal to rho L over A. Now, we know the resistance, is that right? And we know the area of cross section. Well, and therefore, can you find the length of the conductor? Well, we don't need the length. We got R, we replace R by, what is our R? 30L. So 30L equal to rho L over A, and the length will cancel. We get therefore rho equal to 30A, and that will be 30 times area of cross section we know is 7.1 times 10 to the negative 4, and that is 0.021 ohm meter. So this is what we were after, rho. So look at the path we took. We used the electric field to calculate the resistance of the conductor in terms of L. And when that resistance is brought down here in this equation, the length got cancelled, and we could now solve for rho, the resistivity of that conductor. Okay, let's do another problem. A certain light bulb has a tungsten filament with a resistance of 19 ohm at room temperature, that is at 20 degrees Celsius, and 140 ohm when hot. Find the temperature of the filament when it is hot. In other words, this is the resistance at 20 degrees Celsius. That means that is R20. This is the resistance at a high temperature T. So this is RT. What is the relation between resistance at a particular temperature related to resistance at 20 degrees Celsius? RT equal to R20 times 1 plus alpha T minus 20. And you know R20 is given to us, RT is given to us, the resistance at T degrees Celsius is given to us. We need to find that temperature T. Alpha, this is tungsten, so we can go back to our table and obtain the value of alpha. Alpha for tungsten. Now we have RT equal to R20 times 1 plus alpha times T minus 20. Now we know RT, we know R20, we know alpha, therefore we can solve for T. Using all those values, alright, can you simplify this equation and solve for T? I have 1 plus 4.5, look at what I have done here. I have taken this quantity inside the square bracket, that is this, equal to 140 divided by 19, that is 7.37. And now 1 plus 45 times this quantity. Now this one I took from the left to the right, 7.37 minus 1 is 6.37. And what you need to do is distribute this quantity, there you are, T minus 20, see, rather than distributing, T minus 20 equal to 6.37 divided by this number. And that's easy to do it on your calculator. What is 6.37 divided by 4.5 times 10 to the negative 3? You must do it and make sure that you have that value. Or if I'm wrong, tell me about it. So you get T minus 20 equal to 1415.6. And now take that negative 20 to the right side. Therefore T equal to 1435.6 degrees Celsius. You can see simple use of that equation will solve that problem for you. Okay, we will now talk about an electric cell. Now I showed you a simple electric cell. Let's discuss more about electric cell. Now what is an electric cell and how is it made? In order that an electric current may flow continuously, the potential difference between the two plates needs to be maintained. And in the example I showed you, I had a sulfuric acid with copper and zinc electrode. It is the chemical action between the electrodes and the solution, the acid, that builds and maintains that potential difference. Now this can be achieved only if negative charges can be removed from the positive and deposited back in the negative. You see, as negative charges drift from the negative plate to the positive plate, in order to maintain the potential difference, you need to remove negative charges from the positive and put it back in the negative. So this is the external conductor, and you need to do this internally through the cell, and that is what the chemical action in the cell does. This can be done chemically by placing two metal plates in a suitable chemical so that electrons may be removed from the positive internally and deposited back on the negative, so that the charges will now be moving in a closed path. You see, in order to maintain the current, as negative charges keep moving from the negative to the positive externally, you need to move the electrons from positive to negative internally through the cell. Then only the electric current will keep on flowing. Now, here is what a situation I showed you. This is the zinc, that is the negative plate. Copper, that is the positive plate. When you connect them externally, negative charges will move from zinc to copper externally and from copper to zinc internally, so that the potential difference between the two electrodes are maintained. Now, such an arrangement is called an electric cell, which very often people call a battery. Now remember, a battery is a collection of cells. In fact, a collection of anything can be called a battery. Is that right? Have you heard of a battery of soldiers? Yes. So battery is actually a wrongly used word. It's the electric cell is the correct word. The conducting plates are called electrodes. Zinc is the negative electrode and copper is the positive electrode, and the solution, the acid in there, is called the electrolyte. So the basic parts of a cell has electrodes and electrolytes. Now, a simple cell can be produced by dipping a copper plate and a zinc plate in dilute sulfuric acid, as I showed you. And a cell is represented by the symbol. Look at the symbol for the cell. The positive pole of the cell is the long thin line, and the negative end of the cell is a short thick line. Now don't confuse it with the capacitor notation. What is the symbol for a capacitor? Just two parallel lines. Alright? Okay. When the negative pole of the cell is connected to the positive pole, electrons drift from the negative to the positive externally through the conductor, and from positive to negative internally through the cell. If the closed chain is broken, the current will cease to exist. The chemical action between the electrode and the electrolyte, what does it do? What is the cell? Now here, I have a cell in here. This is a cell. There is a chemical inside, and there is a positive electrode and a negative electrode. Now what does the cell actually do? The chemical action between the electrodes and the electrolyte will build and maintain a potential difference between the two plates. So there is a potential difference between the two plates or the two electrodes, the positive electrode and the negative electrode. I can now measure it by using a voltmeter. If I connect a voltmeter across the cell, that voltmeter will measure that potential difference, which is built and maintained by the chemical action. And this potential difference, which is built and maintained in the cell, is actually called the electromotive force, in brief, EMF of the cell. So a cell has an EMF, electromotive force. In other words, when the cell is connected externally by a conductor, What is the motive for electric charges to flow? Is provided by that potential difference. That is why it is called the electromotive force. It motivates the electric charges to move. So the cell has an electromotive force. We will represent it by E. And what is the unit for measuring electromotive force? It is volt, because it is a measure of the potential difference. Alright, when the cell drives a current in an external circuit, the current also passes through internally through the cell. Now, therefore, what does this E really represent? The electromotive force. The electromotive force can be considered to be the total energy the cell makes available for electric current to be driven externally through a conductor and internally through the cell. That means when current flows, energy is used to drive current externally through the conductor and also internally through the cell. The electromotive force is actually the sum of the two energies. Energy that is available to drive current externally and also to drive current internally. Now, only the remaining, that means, so part of that energy, part of the electromotive force is used in driving current internally through the cell. That means only the remaining is available to drive current externally when there is a conductor connected externally. The potential difference between the poles of a cell then becomes less than E. I want you to understand this very well. I will demonstrate that in a minute. You see, if you now connect this cell to a voltmeter, it will measure the actual EMF of the cell. But if you connect a conductor across the cell, which will then allow a current to flow, the voltmeter reading will fall. The voltmeter reading will be less than the EMF. Why? Because the voltmeter then will read the potential difference across the conductor, which is a measure of the energy used in driving current in that external conductor. Why it is less? Because part of the EMF is used in driving current internally through the cell. Okay. Now, potential difference can be measured using a voltmeter. Now, let me see if I can demonstrate that to you before I draw the diagrams for you. Here I have a cell. Actually, this is a battery. It's a combination of some cells. It's got its positive pole, negative pole. I'm going to connect it to a voltmeter and see what the voltmeter reads. I'm connecting it to the voltmeter. I want you to watch what the voltmeter read. Now, what does the voltmeter read? It's read 5.92 volt. Now, what does it tell you? This is the EMF of the cell. When you connect a cell directly to a voltmeter, what the voltmeter reads is the EMF. Now, I'm going to connect the cell to an external conductor. You are familiar with this. Now, I have chosen 1 ohm. This is on now. Everything else is off. So, if I now connect this cell, I think the positive and the negative, I'm going to connect it to here. That means the cell is going to drive a current through that external resistor. Now, see what happens to the voltmeter reading when I do that connection. Well, I hope I will be able to keep them there when I do the connection. Alright? So, hold your breath. I'm going to make this connection now. That's is going to go to one end of this resistor. There you are. And I take a connection from the other pole of the cell to the resistor. Okay, see what happens to the voltmeter reading? The voltmeter reading now says 4.84 volt. Now what does that mean? Now the cell is now driving a current. This cell is now driving a current in this resistor. Now what the voltmeter reads is the energy used in driving the current through the external resistor. What happens to the rest of the energy? The rest of the energy is used in driving current through the cell. That is what I was telling you. Now, if I remove this connection from the conductor, you can see the voltmeter reading should go back to 5.9. But apparently it didn't, because this cell is a very old cell. It takes some time to recover. Now, when I re-establish the connection to the conductor, so you can see what I'm doing. I'm now putting the conductor back in the circuit. The voltmeter reading now dropped. This is now the potential difference between this conductor. So what the voltmeter is now reading is the potential difference between the conductor, which is less than the EMF. All right? I'm going to now explain that on the board. Let's so when the voltmeter is connected across the cell, what the voltmeter reads is the EMF. We now say that the cell is in open circuit. It is not driving a current in an external circuit. So how do you measure the EMF of a cell? Connect a voltmeter directly across the cell. That will be the measure of the voltmeter, will be the EMF. When the cell drives a current in an external conductor, if you now allow the cell to drive a current in an external resistor, like I showed you, the voltmeter reading will now be less than the EMF. And we now call it the terminal potential difference. The potential difference between the ends of the resistor. So this terminal potential difference V, which is less than E, is a measure of the potential difference between the ends of this resistor. If we now consider the current flowing internally, externally through the conductor and the whole path, we can now consider three different circuits. The internal circuit, the current flowing through the cell. External circuit, the current flowing through the external resistor, and then the whole circuit. So look at this. I'm going to look at the internal circuit, external circuit, that is through the resistor, and then the whole circuit. We can actually summarize the statements about these three different circuits using Ohm's law. Now here, when the cell is connected to a voltmeter without connecting to the external resistor, you see, if this external resistor is not there, the voltmeter will read the EMF. But when you have an external resistor connected, now what the voltmeter now reads is the potential difference between the ends of this resistor. So V is the potential difference that drives current in this external resistor. That means, and E minus V, what does E minus V stands for? E is the EMF of the cell. And the EMF is a measure of the total energy the cell makes available to drive current externally and internally. So E minus V is the potential difference that drives current through the cell. That means the cell has to drive current within itself, and a certain amount of energy is used to do that, and that is E minus V. And E, the EMF, is the potential difference that drives current externally as well as internally. So E is used for external circuit and internal circuit. V is used only for the external circuit, and E minus V is used for internal only. If you notice, if you add V to E minus V, this is external, this is internal, add the external to internal, you get the whole external plus internal. Okay, let's use Ohm's law to express these three situations. If I is the current that a cell drives through the external resistance, so this is the current I that goes through the external resistance, then the same current I will pass through internally through the cell as well. Is that right? If a current I passes through the external resistor, the same current will have to pass internally through the cell also. Now, if the cell offers a resistance, well, does the cell offer a resistance? Yes. If the cell does not offer a resistance, then there is no need for spending energy to drive current through the cell. We said E minus V is the energy used for driving current internally through the cell. Now, if an amount of energy is needed to drive current internally through the cell, it means the cell offers a resistance for the flow of current. And we are going to represent that resistance offered by the cell by the lowercase r. So distinguish between uppercase R, the external resistance, lowercase r, the internal resistance. Alright, now we're going to represent the internal resistance. Look at this. We will put a circle with the symbol of the cell and the symbol for a resistor, and this is the representation for the internal resistance. So the current I flows externally through the uppercase R and internally through the lowercase r, the internal resistance of the cell. And we can now use Ohm's law in both these situations. Let's use Ohm's law to write down equations. For the external circuit, a potential difference V, remember that potential difference V is the potential difference between the ends of this resistor, drives a current I in the resistor R. What is the equation for that? V equal to IR. And this is the equation for the external circuit, for the external resistor. Alright, V equal to IR. For the internal circuit, the potential difference that drives current internally is this E minus V. That will drive a current I through this internal resistance R. And what will be that equation? A potential difference E minus V drives a current I through the internal resistance R. Therefore, we have E minus V equal to I times small r, and that is the equation for the internal circuit. So this is the equation for the external circuit. This is the equation for the internal circuit. And if you add these two, you get the entire internal plus external. Alright, so E minus V equal to IR is for the internal, which I have enclosed in a circle. For the whole circuit, the EMF E drives a current I through a total resistance of R plus R. the total resistance for the whole circuit is now R plus R, and that will be E equal to I times R plus R. In fact, if you add equation 1 and equation 2, you will get this. The external circuit, the internal circuit, this is external plus internal. Now, let's divide equation 2 by equation 1. Let's take this equation 2 and divide it by equation 1 and see what we can produce. Look at this. When you divide, this E minus V will be divided by this V. Left side of this equation divide by the left side of that equation will be equal to I times small r divided by I times big R. So E minus V over V equal to I times small r divided by I times capital R. And now I and I will cancel. The left side can be written as, look at the way I'm going to simplify this. This will be E over V minus V over V. That means E over V minus 1 equal to, cancelling i's, gives you R over R. And I can now obtain an equation for the internal resistance of the cell. Therefore, this small r equal to this big R multiplied by E over V minus 1. And this is an equation that will help you to calculate the internal resistance of the cell. Now, what do you do to do that? First of all, exclude the external resistor. First, connect the cell directly to the voltmeter without any external resistor. Measure the EMF E. Then connect an external resistor R, and then you know the voltmeter reading will go down. That is your V. Measure V, and you can use those values to calculate the internal resistance of the cell. In fact, if you come to do a lab here, we will be measuring the internal resistance of a cell in the lab using this formula. We can measure the internal resistance of this cell. Well, although it is written here as the battery, the internal resistance of this cell can be measured. Now watch, this is a switch. If you open the switch, then the external resistor is excluded. The reading of the voltmeter then will be the EMF. So, if you now, the voltmeter reading when the switch is open is the EMF. That means that is the total energy available for current to flow internally and externally. And now if you close the switch, the current is now flowing externally. What will the voltmeter read? The voltmeter will then read V, the energy used for driving current externally. And now, if you know the value of this R, when you do it in the lab, in place of the lamp here, we will be using a known resistor. So you know the value of this R. We have measured E, the EMF of the cell. We measured V, the terminal potential difference when the cell drives a current through a known resistor R. We can calculate the internal resistance as R equal to the external resistor multiplied by EMF divided by the terminal voltage, that is this V, minus 1. Well, I'm going to stop this part of the lesson here. We will do some problems using these concepts and then talk about another concept, which is the energy in an electrical circuit, in a third part of this lesson. All right?